Welcome back to the Rock the JVM studio. I'm Daniel, and in this video we're going to be talking about Akka Typed, and in particular about the pipe pattern and how it can improve our life. Now this video is more of a beginner-friendly video, so this assumes that you're getting started with Akka Typed, but you know some of the actor's first principles, which we discussed in the previous video where we talked about how we can make stateful and stateless Akka Typed actors. So as always, I'll recommend that you code with me in this video, and whenever you need to refresh your memory about these concepts, just refer back to this video or to the article version at the blog with the link in the description. So if you're ready, give this video a thumbs up and let's get started. So that being said, let me get back to my code, and this video will assume that you have Akka Typed set up in your project, and to that end I'm going to go to build.sbt and I'm going to show you what I have here in my configuration. So I have Akka version 2.6.5 in my project, although at the moment of this recording there's probably a newer version 2.6.9 or 10 or something like that. The patch version is not that important. The important version is 2.6. So we're going to be using 2.6 in this video. And the library definition is com typesave Akka %% Akka actor typed. And then you would add this Akka version here in your library dependencies. So if you don't have it in your project, add a new SBT project with the favorite tool of your choice and add the Akka typed actor library definition to your library dependencies. So that being said, I've created a small object here, and I'm going to add a main method just in case we need to test anything, and I'm going to show you how we can pipe things to an actor. And by piping things, I mean handling results of asynchronous computations. And the principle that we're going to rely for this video is the principle of actor encapsulation. So you probably read about Akka actors, and encapsulation means that the state of an actor, which is an entity that is scheduled to run on a thread at some point, the state of this actor is inaccessible from the outside, even in a multi-threaded or distributed environment, and you can only communicate with an actor via a message exchange. However, in real life, actors that we create may not necessarily block on resources while handling a message. They might call asynchronous services, and these services can break actor encapsulation because handling an asynchronous response happens on some thread, which is potentially a different thread than the one that just took control of the actor. Now, I've talked a lot and I've written very little. Let's run on a realistic example. So let's imagine that we are designing some kind of service which performs phone calls, much like a Twilio-like service. Now, I'm going to define an object here that I'm going to call infrastructure. So imagine that whatever we write here in this infrastructure object, you're being given, all right? So you can use this infrastructure object as an API. And this infrastructure object has a bunch of private parts. I'm going to define an execution context on which we can run futures. So I'm going to define a private implicit val execution context. And I'm going to create an execution context myself. I'm not going to use the global execution context. In Scala 2.13, the global execution context can create blockers with chained futures. So starting with Scala 2.13, I always create an execution context myself. I create an execution context by execution context from executor service. And here we can use the Java API to create a thread pool. So I'm going to say executors plural, and I'm going to hit Alt-Enter or Option-Enter to import that, and I'm going to say new fixed thread pool, and I'm going to inject a bunch of threads here. So I'm going to spin up an execution context from a Java thread pool. Now, this execution context will serve as a platform for running futures, and this infrastructure object that I'm going to define here will expose an asynchronous service that will access a bunch of data from a fictitious database. So I'm going to define a database, private val db, and this will be a simple map of names to phone numbers, so a string to int. And I'm going to define a map as Daniel to a phone number like 123 and a bunch of more entries, Alice 456, and then let me add another one, let me say Bob with the number 999. Okay, so this is the fictitious database, the external resource that we are going to access. And the only API that you're given in this infrastructure object is a method definition that I'm going to call async retrieve phone number. And you pass a name as a string, and you return a future int. And the implementation here, let me import Scala concurrent future, and let me run a future. So I'm going to say future, and I'm going to access DB with that name. So the implementation here is unknown to you. You're given just this method definition that given a name, you return a future containing a phone number associated to that name. Now, assuming we're designing an actor which can receive a command to initiate a phone call to a person. This person can be a customer or a friend or whoever your application logic designs it to be. Now, this actor would call this infrastructure's external service, namely this async method, and upon obtaining the phone number, it would initiate a call. Now, let me create a quick implementation. So I'm going to define a val. Let's call this phone call initiator. And I'm going to call v1 because we're going to create a bunch of versions to this actor. And this v1 is an actor described by behavior. So I'm going to import behavior, and this will be a behavior typed with a certain kind of message. And prior to defining the actor, we need to define its protocol. So I'm going to create a trait here. I'm going to define a trait. Let's call this phone call protocol. And I'm going to define a case class. Let's call this find and call phone number for a name. And this extends the phone call protocol. So I've defined the protocol that this actor will respond. Currently, it contains a single message. And this phone call initiator actor is a behavior of this phone call protocol type. All right. So the actor is typed with phone call protocol, meaning that it can only accept messages that extend this phone call protocol. And I'm going to make this actor hold some internal state by keeping track of how many phone call successes and failures it has accrued so far. So I'm going to create that with behaviors. So notice behaviors plural. And I'm going to import behaviors from the Scala DSL package. And I'm going to say setup. And given a context, I'm going to start creating some mutable variables. So I'm going to define a variable. Let's call this number of phone calls, starting with 0, and another variable. Let's call this and failures, starting with 0 as well. Now, I'm pretty sure you're well aware. You might watch the previous video where we discussed stateful and stateless actors, where I give more details on why this structure is important. Behaviors.setup takes a function from an actor context to a behavior that this actor will have upon starting. So I'm going to return another behavior here. I'm going to say behaviors.receiveMessage. And receive message takes a function from a message to another behavior that the actor will have post receiving that message. And I'm going to pass a partial function here to say case find and call phone number for a name. And in case I get a message of this kind, my job as this actor would be to call this asynchronous service. So I'm going to call infrastructure.async retrieve phone number to obtain the actual number associated to that name and actually perform the phone call. And here we're just going to perform a dummy implementation. So I'm going to create a val. Let's call this future number. And this future number will be of type future int. And I'm going to call the asynchronous service. So I'm going to call infrastructure.async retrieve phone number for that name. Now, this thing is a future, and because it is a future, we cannot really inspect its state. We can only perform callbacks on it, or we can transform its results. So we can say future number on complete. So I'm going to say future number.onComplete. And I'm going to pass a partial function from the potential result that that future can contain. So I'm going to say case success with a value, and I need to import Scala util success because the success is a subclass of the try type. So in case we get a success with a number, I would actually perform the phone call here. So perform phone call. Now, for this simplified example, I'm just going to log something. So I'm going to say context log info, and I'm going to write initiating phone call for, and I'm going to inject number here. Okay, and as a result of me performing the phone call, I'm going to also mutate my state. So I'm going to say n phone calls plus equals 1. And at the end of this feature, I'm going to return behavior same, but only after I've handled it. So I'm going to say behavior same. But I also need to handle the failure case. So I'm going to say case failure with an exception. And failure is not part of the automatically imported packages. So I'm going to import scala-util failure as well. And here I would log the failure, or I would display an error on the phone, on the UI if I have something, or something along those lines. So I'm going to log the failure. So I'm going to say context log, and I'm going to add the error call here, and I'm going to say phone call failed for name, and I'm going to inject it here, and I'm going to also inject the exception just in case it is useful for us. And I'm also going to increment the number of failures. And at the very end, I'm going to return behavior same. Now, in order to run this onComplete callback, I will need an execution context. And so I'm going to define an implicit val execution context as context.system.execution context, just to be able to run this callback on a thread pool, and the thread pool is backed by the actor system. Now, on that note, I also think that there is an execution context directly attached to the actor context, so that we don't need to invoke the system again. So you can simply say context.execution context, and my code is still green. All right, so this is basically our actor, which can invoke an external service, and it can also handle the result of that future. Now, what is the problem with this implementation? The problem is that future callbacks, such as onComplete here, happen on another thread. Now, this thread may or may not be the one that's actually handling the message at this point. In other words, each of these lines which mutate internal state, like line 43 and line 47, are race conditions, because the variables here may be mutated by multiple threads that might invoke the external service after receiving some message. All right. So in this case, we have broken the actor encapsulation because we have race conditions. This is a problem. A second drawback is that because changing the actor state here at lines 43 and 47 happen in a future call, we have no choice but to make this actor stateful with variables, which may or may not be to your taste. It certainly is not to my taste. And we can solve that. And the goal of this video is to show you the pipe pattern to solve this problem. Now, the actor encapsulation breakage is a major problem because the Akka model, the actor model, guarantees actor encapsulation up to a point. And this is that point. And it's up to us to still enforce actor encapsulation after invoking external services. And thankfully, through the pipe pattern, there is another way which is completely safe, both from a type perspective and from a multi-threading perspective. Now, the question that inspired the pipe pattern is the following. Why do we need to handle the result of this future at all? Can we just forward the result of this future back to me, to this actor, as a message, which can be later handled in a very thread-safe way? Now, this technique is the pipe pattern, is the ability to forward the result of a future back to me as a message. So we are going to automatically redirect the contents of this future number back to this actor as a message which it will receive later. Now, there are two important aspects to this approach. A massive benefit is that the result of the future will be later handled by the actor as a message, which is atomic. And the benefit is that we don't have the encapsulation break anymore, since handling the result of that future will be handled as a message in a thread-safe way. Now, another benefit, which is also a responsibility to us as programmers to implement correctly, is that the result of the future, which is in this case of type int, needs to be forwarded to the actor in a way that it accepts in terms of its protocol, because the actor does not accept int messages, but it only accepts the phone call protocol message. So we need to also transform this future into something that the actor can accept, and we can later handle that as a message. So here goes. In order to make this pipe pattern work, the result of our infrastructure asynchronous call, this thing, needs to be transformed into a message type that the actor supports. So we need to create two more adapter messages. I'm going to go up top here, and I'm going to define two more case classes, and I'm going to call that initiate phone call to a number, and this extends phone call protocol, and a case class, let's call this log phone call failure, with a reason that is a throwable, and this also extends phone call protocol. Now, depending on the result of this future, depending on whether the future was successful or not, I'm going to transform that result into either an initiate phone call message that I'm going to send myself, or a log phone call failure that I'm going to send with myself. And in this way, we can make the actor send future results back to itself later and handle the new messages. But first of all, let's go ahead and test this one to make sure it's correct before we go about the refactor. So in main here, I'm going to define an actor system, or let's call this the root actor, because I'm going to refer to this actor system by its root actor node. And I'm going to create an actor system from Akka Typed, backed by phone call initiator v1, and I'm going to call this phone caller. All right. Now, I'm going to send a bunch of messages to this root actor. So I'm going to say root tell, and I'm going to say find and call phone number with a name that is in the database, for example, Alice. And I'm also going to tell root tell find and call phone number with somebody that's not in the database. I'm going to say Akka, for example. All right. So we should be seeing two different log lines here. And let me go ahead and add a thread sleep, after which I'm going to also terminate the actor system to make sure that the resources are closed cleanly. So I'm going to say root.terminate. So let me go ahead and run this application, and let's see what kind of log lines we see in the console. It's going to take a couple of seconds for me to compile, and let's look at the logs. Okay, so we have initiating phone call for 456, meaning that the actor could easily retrieve the phone call for Alice after the asynchronous call, and after handling the result of its future, we are seeing this log to the console. And also we have a phone call field for Akka, because there's no such thing as an Akka entry in the database, and we get the Java util no such element exception with key not found. So we get the correct results to the logs. Now, if it just so happens that you don't see these logs to your console, it may be because you don't have the appropriate SLF4G correct configuration there. If that's the case, then change these context log infos and context log error to plain print lines, just to make sure that everything works. All right. Cool, so our actor works correctly. Let's go about the refactor with the pipe pattern. So I'm going to define another value. I'm going to shamelessly copy most of this stuff, and I'm going to call phone call initiator version 2. And I'm going to use basically the same construct here. Behaviors.setup with context. I'm initiating the initial variables here with the same execution context. However, instead of this onComplete thing, I'm going to call a very interesting structure. So instead of a future number onComplete, I'm going to say context.pipe2self. And pipe2self takes two argument lists. The first argument is the future that I want to pipe, in this case, my future number, and the other argument list is a function that processes the result of that future in the form of a try result to the kind of message that this actor supports. So I'm going to say pipe2self with future number, and I'm going to add a partial function that will transform the result of that future from a try int into a phone call protocol. So in case I get a success with a number, I'm going to send the following message back to me in the form of initiate phone call with that number. And in case I get a failure with an exception, I'm going to say log phone call failure with that exception. All right. Now, these messages are going to be sent back to me later. And pipe2self is fully thread safe. So there are no resource leaks or raise conditions here. I'm going to simply call behavior same at the end of this case, and I also need to add the other two cases. So I'm going to handle the case for initiate phone call number. And in case I get an initiate phone call number, I'm actually going to perform the call. So I'm going to copy this behavior back, and I'm going to say behavior same. And in case I get a log phone call failure with an exception, I'm going to do exactly the same as my previous actor used to do. So I'm going to copy the implementation, and I'm going to return behavior same as well. Now, in this case, I am not going to log the name because it's not part of the phone call failure. You could also include this here. So if you want to modify your case class to include the name for which the phone call failed, you can feel free to do that, include that in the case class and inject it here in the pipe2self call. So this is our phone call initiator v2, and notice that in this case, state mutation happens as a message handler. So there are no more race conditions. Now, let's also test it to make sure that it performs just as well. So I'm going to name this phone call initiator version 2, and I'm going to run this application just as it is with a phone call initiator v2, expecting basically the same logs to my console. And notice that we have an initiating phone call for 456, and we have phone call failed for, and I missed the name. I'm going to cut this out here with the same kind of exception, key not found with Akka. So notice that the key is also included in the error message. All right, brilliant. So we've avoided the massive problem of actor encapsulation break. This pattern, this pipe pattern, now also enables us to make the actor stateless if we wanted, because now changing actor state happens in a message handler. So we can further refactor this actor into a method. So I'm going to define a method. Let's call this phone call initiator v3. And this method will now have as arguments what we used to store as state. So I'm going to say n phone calls as int starting with 0, and n failures, which is an int starting at 0. And this is a behavior of phone call protocol. Now, because we aren't going to use any kind of variables here, we do not need behaviors.setup. So I'm going to eliminate it all together. So I'm going to say behaviors.receiveMessage in this case, or receive if you want to also keep the actor context. So I'm going to say behaviors.receive, and I'm going to pass in the 2arg function here, context and message. And given these two, I'm going to run a pattern match on my message. So I'm going to say message match, and I'm going to run the exact same 3 cases that I'm going to copy and paste them here. Now notice that my compiler now helps me where I used to modify my mutable state, and instead of mutating state with plus equals and returning behavior same, I can return a new behavior by calling this method again. So I'm going to say phone call initiator v3 with n phone calls plus 1 and the same number of failures, which is a new behavior object. And same here, I'm going to call phone call initiator v3 with the same number of phone calls and failures plus 1. All right, so notice that this actor not only handles the results of futures correctly, but it's also stateless, it's functional. we do not have any mutable state. We don't have any variables, and we don't have our execution context there. So just to make sure that this actor works correctly as well, I'm going to use v3 here, and I'm going to invoke it just like that because the arguments start with the default value of 0. And I'm going to run my application, and I'm going to expect the same kind of logs to the console. All right, so we have initiating phone call for 456, and again, phone call failed, no such element, key not found, Akka. So in this video, we explored how the pipe pattern solves a potentially serious problem when handling future calls inside an actor's scope, how it can repair it, and as a bonus, how it can make an actor stateless even while handling results from external asynchronous service. If you like this video, go ahead and give me a thumbs up for this video and subscribe to the channel for more videos like this, and give me your feedback in the comments. I read every single one. Also, go ahead and follow us on Twitter and LinkedIn. Check out the blog and the website. We have hundreds of hours of video and written form at rockthejvm.com. Until next time, I'm Daniel, signing off.